Bismillahirrahmanirrahim. Dear students, I welcome you all in this course on data communications and computer networks. This course is being offered by Department of Computer Science at ComScience University Islamabad Lahore campus. And this is our lecture number 2 of asynchronous mode of learning. In this lecture, we will talk about TCP's flow control mechanism. It's very important to control the rate at which sender is sending data to the receiving machine, and it should not be at a faster rate than the application at the destination side, right? And then we'll talk about the problems associated with this flow control mechanism, such as silly window syndrome and sender sending data in small sizes. Then we'll talk about TCP Connection Establishment mechanism. This seems a very simple topic, but it's very thrilling since there are many different types of attacks that makes TCP connection management establishment mechanism vulnerable. Then we'll also talk about the principles of congestion control, and we'll compare end-to-end and network-assisted congestion control approaches. The learning outcomes of today's lectures are to make you understand the flow control mechanisms of TCP, its importance, and the problems with the flow control mechanisms of TCP and their possible solutions. At the end of this lecture, you should understand and value TCP connection establishment mechanism. Since we have to establish a TCP connection between the two machines before transmitting any data on it. So it's very important to see how TCP establishes a connection with the other machine. And you'll be able to judge the effectiveness of the principles of congestion control by comparing end-to-end and network-assisted congestion control. So before discussing today's lecture, let me quickly review what we have covered in the last lecture. So in the last lecture, we talked about the TCP principle and services provided by the transport layer. And then we talked about the demultiplexing and multiplexing process at the transport layer with the help of sockets. Then we talked about the two very important, introduced ourselves to two very important protocols at the transport layer, transmission control protocol and user datagram protocol. We discussed the header of UDP, user datagram protocol, and transmission control protocol in detail. Then we discuss general reliability delivery mechanisms such as stop and wait, automatic repeat request, go back and automatic repeat request, and selective repeat, automatic repeat request. Then we also established a case to have a pipelined reliable data delivery mechanism, and we identified that this we can achieve with the help of go back and automatic repeat request and stop and wait automatic repeat request. And then we talked about the reliable data delivery mechanisms offered by TCP. And we did discuss that TCP trigger a retransmission whenever there is a timeout or there are triple duplicate acknowledgements. So today we'll talk about TCP flow control mechanism. This is the first topic that we'll discuss. And whenever we establish a connection between the two ends using transmission control protocol, the receiver maintains a buffer, allocates a buffer to receive whatever data that is coming from the sender side, right? And the purpose of establishing this buffer is to make sure that the sender should not overflow the buffers, or sender should not send data at a rate faster than the application process at the receiver side. So what if the application is relatively slow at reading the data? In this case, the sender can very easily overflow the connection's receive buffer by sending too much data to it quickly. So what I'm saying is, for example, this is the buffer that we are maintaining, and if the sender keeps sending on the data, So this buffer will start, getting full, and here the application is slow at reading the data. So application is slow at reading data from this buffer. So the sender side is keep on sending the data, but application is slow at reading the data. This means we will end up with a small buffer size on the receiver side, and sender needs to slow down accordingly. So TCP provides a flow control service to its applications to eliminate the possibility of sender overflowing the receiver's buffer, right? So because the sender has to match the receiver's applications, reading speed. So TCP can, guarantee this by using this flow control mechanism, and by having a sender maintained a variable called receive window. So this receive window here indicates the spare room in the buffer, the space that is available in the buffer. So, so basically, flow control is a mechanism to make sure that sender won't overflow receiver's buffer by transmitting too much, too fast. And you can say it's a speed matching service, where the sender is matching the send rate to receiver's application drain rate. So this drain rate means that the rate at which the application is reading data from this buffer. Now, in order to implement this flow control mechanism, the receiver maintains certain variables. For example, receiver will maintain the last byte received and last byte read. So this last byte received or this last byte read is the number of the last byte in the data stream read from the buffer by the application, and this last byte received is the last byte in the data stream that has arrived from the network and has been placed in the receive buffer at the destination or machine B. So so if I take the difference of these two, this should always be less than the receive buffer. So by the way, this last byte received, last byte received minus last byte read should always be less than equal to this receive buffer. Should be less than equal to receive buffer. Okay, so why? Because this last byte read and last byte received is basically indicating, this TCP data in the in the receiver's buffer, right? So this is the last byte. This is the last byte read, and this is the last byte received, right? So this, if I take the last byte received and the last byte read by the application, this will give me the TCP data that is placed in the buffer at the moment, and this has to be less than the receiver buffer, this total space at the receiver side. Similarly, the sender maintains a receive window, a variable known as receive window. And if you remember, we also discussed this in the TCP header segment. The TCP header segment has a field known as receive window, if you remember, right? And what is the functionality of this receive window, by the way? Yes, you're right. This indicates the available space in the receiver buffer, and sender will not send data greater than the window advertised by the receiver side. So by the way, this receive window is equal to this receive variable receiver window is equal to the receive buffer minus the difference of the last byte received and the last byte read by the application, which is the available source, or which is the data that is placed inside the buffer. So if I take the total buffer space and minus, the data that is available in the buffer, this will give me the available space at the receiver buffer that I can advertise for the sender to send accordingly. Similarly, on the sender side, sender also maintains couple of variables like last byte sent, and last byte acknowledged. Last byte act. Right, so these are two variables maintained by the sender side also. And if I take the difference of last byte sent and last byte acknowledged, so these are the total bytes in the sliding window at the receiver side that are unacknowledged, that the sender is waiting to be acknowledged. And remember, this has to be less than or equal to the available space in the receiver window at the receiver side, and this space in the receiver window at the receiver is being represented with this variable called receive window. So this should be less than equal to received window, right? So in this way, sender will send data according to the buffer space available at the receiver side. But there are some problems with this flow control mechanisms that we need to discuss, right? And let me try to explain these problems with the help of a scenario. So, so what we want to talk about is that what are the problems with this TCP flow control mechanism. So there are two problems, two flow control problems, two flow control problems that I would like to discuss with you. Number one is that receiver is too slow. That receiver application is reading data too slowly from the receive buffer, and this problem is called silly window syndrome. Silly window syndrome. This means that receiver is advertising a silly window size, means very small window size. We'll see what we mean by this in a minute. Silly window syndrome. And the second problem that I want to discuss with you is associated with the sender. That sender's data comes in small amount. I mean, sender is sending TCP segments of small sizes, and this is true, by the way, in case of interactive applications such as instant messaging. And the solution to this problem is given by Nigel's algorithm. So we'll see what is this problem and how Nigel's algorithm tackles this problem, right? So let's talk about the first problem, that is silly window syndrome. So silly window syndrome means that receiver window opens only by a small amount of time, and sender can only send a small amount of data at a time. Why? Because the application, why? Because the application at the receiver side is slow reading data from the receiver buffer. Why this is not good? What's the problem? So the question is, why why silly window syndrome is not good? Okay, so there are two reasons that we want to address this problem and why it's bothering us. Number one, it involves packet header overhead. So it involves packet header overhead. Means what? Means maybe we are sending 1 byte data, but for that we have to send a packet header of 40 bytes. We'll see in a minute with the help of a scenario that what do we mean by this. And the second problem with the silly window syndrome is that that these small size packets, small packets cause more interrupts at a busy receiver. So supposedly the receiver is already busy. That's why receiver's application is too slow reading data from the buffer. So if I'm sending small size packets, means more number of packets to transmit data. This will cause more interrupts at the receiver side. So let's try to understand this problem with the help of an example. So we'll see. First of all, we'll see what the effect of the silly window syndrome is, and then we'll see what are the possible solutions, implementation, how we can avoid this problem. So let's suppose that we have a machine A and there is a machine B, and this is the timeline of machine A, and machine here, the timer is increasing downwards. And initially, machine B advertised a window size of, say, 2500 bytes. Now, in response to this receive window from machine B, machine A transmits a segment, say, having size of 1000 bytes. Then it again sends another segment having 1000 bytes, and then it again sends another segment by looking at the available space in the buffer. How much space is available, by the way, now? What should be the size of this segment from A? Yes, you're right, 500 bytes. Okay. Now what happens at the receiver side? So I assume that that at receiver, by the way, this is the silly window syndrome problem, that application at receiver reads out, say, 1 byte at a time. So this means what? So this means if application is too slow and reading 1 byte, so if application reads 1 byte, so how much space will be available in the receiver window? Yes, you're right, 1 byte. So this means now this time the receiver window, which is machine B, will advertise a window size of 1. And this means what? That A will be transmitting the segment having a size of 1 byte. And if same is the case, next time also that application reads out 1 byte at a time. So this means A will keep on sending small segment sizes. And this will, why this is not good? Because I'm sending 1 byte and 1 byte of data, and I have a packet header size of 40 bytes, for example. And sending too many small packets will further, make this receiver busy. So this will further affect the performance. Right? So what's the possible solution of this problem? So how can we address this problem? The solution to silver window syndrome is, so now I want to talk about its solution. So what do you think? What is the solution to this problem? Where the application is reading data too slow, and that's why the sender is sending small size segments. So the solution is the receiver machine B in this case should not, the receiver should not, don't advertise a window until it opens significantly. Okay, so what do you mean by significantly? So don't advertise a window until it opens significantly means until there is enough space available in the buffer. Then the question is, how much space should be available in the buffer? And then a receiver B in this case should advertise this window. The available space in the buffer should be greater than half of maximum segment size. We know this MSS maximum segment size, or it should be greater than half of the receiver window. So receiver in this case, which is B, will only advertise a window size when its size is greater than half of the maximum segment size or half of the receiver window size. But now the question here is, what are the implementation alternatives? How we can make sure that a sender is not, is not advertising a window until its size is greater than half of the maximum segment size or half of the receiver window size. So the implementation alternative is, how we gonna make sure that this happens is that receiver will send an acknowledgement ACK with receive window size 0. Okay. Let me try to elaborate it with the help of an example. So again, we assume that we have a machine A, and then we have a machine B, and it's the timeline increasing, downwards. And this initial scenario is the same as was in the previous example, where the B will advertise a window size, say 2500 bytes, and in this in response to this, A is transmitting first segment having 1000 bytes, and then another segment having 1000 bytes, and then the last segment will have 500 bytes. Okay, so same is the case, in this scenario also, that application at the receiver side reads out 1 byte at a time. Okay, and in order to avoid the the small segment sizes which was happening without a solution to the silly window syndrome problem. Now, the receiver, instead of advertising window size 1, receiver will advertise window size 0. So now, in this case, receiver is advertising window size 0. And now, since the receiver window size is 0, machine A cannot transmit anything. So now the sender waits for some amount of time and again sends a probe message to this destination machine. So here the sender is sending the probe message requesting to advertise the window size. By the way, the amount of time the sender is waiting to generate a probe message is called persistence timer. Persistence timer. So sender will wait persistence timer. By the way, this is 60 seconds. So sender will wait for 60 seconds and then will send a probe message requesting machine B to advertise the window size, hoping that now enough space is available in the receive window to generate a segment size having considerable size. There is another solution to this problem, right? And that is called delayed acknowledgement. So another solution to this silly window syndrome problem is delayed ACK. But the problem is, or the limitation here is that an acknowledgement should not be delayed not more than 500 milliseconds. So one problem is that one solution to this problem is that B will advertise window size 0, and the sender machine A in this case will wait for persistent timer, which is 60 seconds, and will send a probe message and hoping that now the enough space is available in the receiver buffer. And the other possible solution is that B is delaying the acknowledgement, right? Hoping that by the time it will send an acknowledgement, enough space will be available in its buffer, right? But the problem is with this, or the limitation is that we cannot wait more than 500 milliseconds. Or the second issue here is, the problem is we have to send ACK for every other segment. So we just cannot say that we are not sending acknowledgements. So if we're receiving a segment, we have to generate its acknowledgement, and that cannot be delayed more than 500 milliseconds. So we have to ACK every other segment. What do you think? Why? Why we have to acknowledge every other segment? So I leave this question for our online discussion. So why don't you think about it and come up with your answers in our online sessions, and we'll have a discussion on this point, right? So this is problem number 1 with our flow control mechanism, right? And is called silly window syndrome. Okay, so silly window syndrome occurs when small sized segments are transmitted, resulting in inefficient use of network pipe or bandwidth. For example, suppose that the TCP sender generates data slowly, say 1 byte at a time. Why? Because the window that is being advertised by the receiver is of 1 byte. Okay, so there is another problem that I want to discuss with you. And that problem is linked with interactive applications. Remember, we identified two problems with this flow control mechanism. One was receiver too slow, and the other problem was sender's data comes in small amount. Okay, so let's talk about and focus the second problem here. And this link, this is linked with, by the way, interactive applications. So here I want to talk about the interactive applications that are using, TCP, so interactive applications. Interactive applications such as instant messaging, right? So the problem with the interactive applications is that user sends only a small amount of data. Means maybe such as instant messaging, it sends one character at a time. So what's the problem with these interactive applications? The problem is, so what do we think? What is the problem with these interactive applications? The problem with these interactive applications is 40-byte header we had overhead for every byte sent. So if in instant messaging I'm sending 1 byte at a time, or 1 character, for example, so I have to attach a 40-byte header for it, right? And the solution to this problem is, so what is the solution? What do we think about the solution? The solution to this problem is clumping. So what do you mean by clumping? Clumping means sender clumps data together. Okay. What do you mean by this? This means sender waits for reasonable amount of time before sending. But again, the question is, what do you mean by waiting for the reasonable amount of time? Okay, so let's try to understand the solution with the help of Nigel's algorithm. Nigel's algorithm here. So the implementation of the solution is Nigel's algorithm. Nigel's algorithm. What it says, by the way. So Nigel's algorithm says that send first segments immediately, regardless of its size. So send first segment immediately. And then accumulate data until acknowledgement returns. Accumulate. So we are clumping data. Accumulate data until ACK returns. Until ACK returns, or there is another condition here, or we have data up to half of the sender window size. or the data that we have accumulated is half of maximum segment size. Okay. So I will elaborate it with the help of an example, a scenario in a minute. So let me quickly reiterate the steps. The Nagel's algorithm says that whatever is the first segment, whatever its size is, it should be transferred immediately, and then we should be accumulating the data until we receive an acknowledgement from the receiver, or the data size is half of the sender window or half of the maximum segment size. So what do you think? What's the advantage of Nagel's algorithm? Before we go and discuss it with the help of a scenario, what do you think? What are the advantages? Yes, you're right. Number one is that bulk transfer is not held up. Means if we have data up to half of the center window or half of maximum segment size, I should not be waiting or delaying the sending process. I should send immediately, right? And the second advantage is send data as fast as network can deliver. So, so this means data sent as fast as the network can deliver. So let's try to understand it with the help of a scenario. So we'll take a scenario that involves no solution to this problem, and then we'll see how Nagel's algorithm handles it. So let's assume that we have a machine A, and then we have a machine B, and it's the timeline of these machines increasing downwards. There is the timer indicating the timeline. Okay, and what happens is that whenever a host A has something to transmit, it transmits, right? Say host A transmits segment number 1, then it transmits segment number 2, and say segment number 3, and all the segment up to the window size, right? So this is the last segment in the window. And similarly on the receiver side, machine B receives segment number 1, it generates an acknowledgement, right? This blue lines indicates acknowledgements, by the way, in our scenario. And then it acknowledges segment number 2, and then it acknowledges segment number 3, right? And similarly, it will acknowledge segment number, or the last segment, in this case, which is segment number, say the last segment here. So when it receives an acknowledgement of segment number 1, it will again send another segment, right? And then so on and so forth. And similarly, it will receive this acknowledgement, and this will continue. So what do you think? What's the problem with this approach is? The problem is, by the way, this is a mechanism without Nagel's, right? Without Nagel's algorithm. So the problem is that this byte number 1 contains 1 byte, and the segment number 2 also contains 1 byte, and the segment number 3 also 1 or very few bytes, because we are talking about the instant application where we are sending 1 byte message, or the segment size is small. In the clear disadvantage, as we discussed earlier, is the header overhead here, right? So let's try to see what is the possible advantage if I implements Nagel's algorithm here. So again, assume that we have a machine A, and then we have a machine B here, and this we are talking about an implementation with Nagel algorithm, right? And again, it's this timeline increasing downward, and same is the case for machine B. So timer. Okay, so what it says, look at the solution. It says send first segment immediately. Okay, so whenever we have a segment to transmit, regardless of its size, we will transmit it, right? Say its segment size is 1, and I'm talking about segment 1. Okay, and then machine B will generate its acknowledgement after receiving segment 1. But when A receives the acknowledgement, or A will not send the next segment. So here we are not sending, we are not sending another segment. Segment number 2, we are not sending segment number 3 of 1 byte or fewer number of bytes. Here, what we are doing here, we have to accumulate. So here, accumulated data is sent. Okay, so accumulated data is sent in response to this acknowledgement. So here now sender A is sending a segment supposedly having more number of bytes. Why? Because we are delaying this sending process up to waiting for enough bytes to be accumulated. How many number of bytes? Half the sender window, or half of the maximum segment size, or until the acknowledgement has arrived, which is the case in this scenario, right? Upon receiving an acknowledgement, we are waiting, and now we will send this packet which has more number of bytes as compared to this scenario here, and obviously it will send an acknowledgement B here. Okay, so this is the implementation of Nagel's algorithm. Well, there is a problem with the Nagel's algorithm that I want to discuss with you in the class. So if I look at my bandwidth graph implementing Nagel, so it's like it goes in a linear fashion, and then I'm waiting for enough bytes to be accumulated. So when enough bytes are accumulated, or I received an acknowledgement, then I again send the next segment, and then I again wait for enough bytes to be accumulated. Then I again transmit, and then I wait. Again transmit, and I wait. So there is an obvious, there's an obvious performance consideration here, and I want you to think about it, right? And we shall discuss this in our online session. Okay, so coming back to our slide set. So the second problem with the flow control mechanism is where the TCP sender sends a very small amount of data, and solution is Nagel's algorithm, where the sender sends the first piece of data obtained from the application, regardless of its size. Even if it's fewer bytes, we'll send it, and then we wait for the enough bytes to be accumulated in the sender buffer. So how many number of bytes, right? So half that of the receiver, that of the sender window, or half of the maximum segment size, or until an acknowledgement is received, and we repeat this step until we are done with the communication. Okay. The next topic that I want to discuss with you is TCP connection management. So TCP connection management is a very interesting topic because many of the most common network attacks, including the incredibly popular Syn Flood attack, exploits the vulnerabilities of or vulnerabilities in TCP connection management mechanism. So we would like to see this as well. So here, I should write it here because I'll be discussing it in a minute. So we have to understand it. Why? Because the Syn flood attack basically it targets three-way handshaking mechanism of TCP. So let me quickly recall that a TCP. Let us quickly recall that a TCP sender and receiver has to establish a connection before exchanging segments with each other, right? And for this reason, a server is always listening on a specific port for the incoming connection, and client can initiate a connection by initializing a socket object, identifying the host IP address, means the destination server's IP address, and server's process address, port number. And it's both server and the sender initializes initial sequence numbers and buffers for flow control information that we'll see in a minute. So TCP uses three-way handshaking process, right? Means there are three steps involved in the connection establishment of TCP. The first step is that the client host will send a special segment known as Syn segment, right? So it will send a special segment known as Syn segment to the server by setting Syn flag. Remember when we talked about the TCP segment header, we discussed 6 different flags inside TCP segment header, and we identified a set of 3, R, S, and F. And we said these 3 flags are used for connection establishment, resetting, and termination, right? So this special Syn segment is generated by setting this Syn flag, by setting its value to 1. And it has some initial sequence number, but it has no data associated with it. Why? Because we have not established our connection so far. It's a connection request, by the way. So this special Syn segment is acknowledged by a Syn segment, right? So this Syn segment is generated by the server by setting the Syn flag. And if you remember, there was another flag known as acknowledgement flag. Okay, so it not only sets the Syn flag, but it also set the acknowledgement flag. The server replies with the help of a special segment, which is known as Syn segment, Syn-ACK segment, by setting the Syn flag and also the acknowledgement flag. And server also allocates buffer here. So buffer to receive whatever data coming from the sender side, and it also uses or randomly selects the initial sequence number. And here we have the problem, right? So this initial sequence number or this allocation of the buffer makes TCP vulnerable to a denial of service attack. So this makes the TCP vulnerable to a denial of service, is DOS, denial of service attack. Okay, so which is also known as, by the way, Syn flooding. Okay, denial of service attack means here I'm talking about Syn flooding. So in a minute we'll see what are the possible solutions. So let us first discuss this 3-way handshaking process. And now, in response to this Syn-ACK segment from the server side, the client machine sends an acknowledgement to this Syn-ACK by setting the acknowledgement flag only. And in this case, we can also attach the data with this segment. Since we since we exchange three messages, or there are three steps involved, we call it three-way handshaking mechanism. But there are a couple of questions that I want to raise for our online sessions discussion. Number one is, what do you think? Why are initial sequence numbers needed? So remember, whenever this a special Syn segment is generated by the client machine, it uses a special randomly selected initial sequence number, and same is the case with the reply from the server side. So the question is, what do you think? Why do we need to have this initial sequence numbers, and why we select it randomly? And then the second question that I want to put here for our online discussion is, what do you think? Why is a three-way handshaking why there is a three-way handshake as opposed to say as opposed to two-way handshake. Two-way handshake needed. So what do you think? Why do we have two-way handshake? What if we have a three-way handshake? What if we have a two-way handshaking process where the client is sending a special Syn segment and it is being acknowledged by a special Syn ACK segment from the server side? What do you think? Where we can have deadlocks? Can we have deadlocks? By the way, this is another question for our online session: is can we have a deadlock in three-way handshaking? Or if we are not using three-way handshaking, let's suppose we are using two-way handshaking, what do you think? Can we have a deadlock in two-way handshaking? Right. So we think about these questions, and we'll discuss these questions in our online session. Let's try to understand this TCP connection establishment mechanism with the help of an example here. So let's assume that a client has to establish a connection with the server. So this client will send a special segment, which is called, we know this, which is called Syn segment. By setting what? By setting this Syn flag. And this initial sequence number is generated randomly. And when server receives the Syn segment from a client, because server is listening on a port all the time for incoming connections, it generates a segment by setting Syn flag and by setting acknowledgement flag. And we know this, that this is called Syn ACK segment. Syn ACK segment. And here again, the server selects the initial sequence number randomly, and here is the problem. Here this is why we can have a Syn flood attack here. This is a cause of Syn flooding attack. Okay. So we'll see how in a minute. Okay. So and when this client receives this Syn ACK segment from the server, it replies with a segment by setting the acknowledgement flag, and here we can also send data in this segment. And this is how a connection is established between a client and a server machine. So let's see how we can, what is the Syn flood attack, by the way. So Syn flood attack is among the first documented DOS attack. right? Fortunately, you know, an effective defense, which is called Syn cookie. Syn. So there's an effective defense to this Syn flooding attack, which is called Syn cookies, is available, and Syn cookies are now deployed in most major operating systems. By the way, the details about the Syn cookies are given in request for comments 4987. Okay. So what is this Syn cookie? The Syn cookie is, so now this Syn cookie or a cookie, this cookie is basically a complicated function. By saying complicated, I mean hash function. Hash function used to generate the initial sequence number. So in this case, in Syn cookies or a cookie, the server will generate an initial sequence number using hash function. And this initial sequence number now is called a cookie. By the way, this hash function or this complicated function involves source IP address, destination IP address, source process address port number, destination process address port number, and plus a secret number, right? So you can say that this secret number is known to server only, right? So plus a secret number. So I will take all these values, I'll do a hash function, and whatever the result is called a cookie, and this will be the initial sequence number that will be advertised by that will be the initial sequence number of the Syn ACK segment generated by the server side. Okay, so this carefully crafted initial sequence number, which we call cookie, will make sure that server will only accept connections from the legitimate client. By the way, so the other difference is, so in the previously, without having a cookie, whenever there was a request from the client, server after generating this Syn ACK segment allocates buffer for this client for incoming data. But now in this case, when server generates the initial sequence number using this hash function of source IP address, destination IP address, source port number, destination port number, plus a secret number, it does not allocate buffer. And now server waits for the response from the client side. But here the question is, how does the server make sure that now this response is from the legitimate client? So what the server does is that it takes the sequence number of, which is obviously the last byte number, which is because there's no byte here, y plus 1. It takes the sequence number here, and it again takes the source IP address, destination IP address, source port number, destination port number, plus the secret number, and adds 1 into it, and again it calculates the hash function and see if this number is same to this the sequence number of this acknowledgement as in the third step from the client. This means this is a request from the legitimate user. Okay, so then only server maintains or allocates buffer for the the client side. So what was the problem previously? So when the client was generating a Syn segment, and server maintains or allocates buffer for it and generates a Syn ACK segment. So there's a possibility that malicious clients are sending requests. So this means server will keep allocating buffers for malicious requests, and whenever there is a legitimate client, maybe server resources not available because of this DOS attack known as, because of this DOS, denial of service attack known as Syn flooding. So servers resources not available to provide services to this legitimate client. Okay. Students, the next topic of this lecture that I want to discuss with you is principles of congestion control. So let's try to understand that what do you mean by congestion? So congestion, informally, we can say that too many sources are sending data sending too much data too fast for the network to handle, right? So the flows are from the different machines, and the manifestation of network congestion is that there are packet losses because the buffer overflow at the router, or maybe at the destination, and due to the increased end-to-end delay because the RTT has increased. Okay, so these two things will indicate that there is a congestion in the network, and whenever there is a congestion in the network, means there are packet losses or there is increase in round trip time. This results in unfair and poor utilization of network resources. Why? Because resources used by route packets before they were lost, we are wasting it, and there are unnecessarily transmissions in the network. Then poor resource allocation at this results in poor resource allocation at high load. So we really need to come up with a mechanism to handle congestion in the network. By the way, this congestion is different from flow control. As a savvy network reader, we need to make a clear difference between the two, and that we'll do in the next lecture also. Let me present to you the historical perspective of this congestion. The first congestion happened in 1986 when internet had its congestion collapse, when there was a connection between the LBL and UC Berkeley and of 32 kilobits per second, and it drops to 40 bits per second with the factor of 1,000, right? So when this congestion happened, then when Jacobson proposes TCP congestion control mechanism to achieve high utilization, to avoid congestion, and to share bandwidth with multiple hosts in a fair manner. So there are two congestion control approaches that we'll discuss in the next class. Let me list these two approaches and discuss it briefly with you. One is called end-to-end congestion control, where the core network means the routers are not sending any explicit feedback, right? So, and the congestion is observed by the end systems, and the congestion is observed as a loss of a packet if acknowledgement is not received, or a delay means the RTT has increased. And by the way, this is the approach that is taken by the TCP, and this is the approach that we'll be exploring in detail. And the other possible solution or the approach of, for this network control, network congestion control is network-assisted congestion control, where the routers are sending feedback to end system by sending choke messages or by sending explicit congestion notifications, ECNs, right? So this explicit congestion notifications is an alert for the sender to slow down the sending rate. Why? Because a congestion has happened. So we'll discuss this congestion control. I have just introduced congestion control in this lecture, so we'll talk about the possible congestion control approaches and its effect on the network in the next class. So that's it for today's lecture. So let me quickly revise what we have covered in today's lectures. We have talked about the flow control mechanism that a receiver has to maintain a receiver buffer in order to make sure that sender matches the its sending rate with the application of the receiver side, that sender is not sending data too much data too fast to overflow the receiver's buffer. And we also looked at the possible problem with the flow control mechanisms of TCP, like silly window syndrome and sender sending small amounts of segments of small sizes, and we try to look at its possible solutions. Then we talked about the TCP connection management mechanism protocol. It's a three-way handshaking process where the client sends a special SYN segment, and by setting SYN flag, and server replies it with the SYN ACK segment by setting SYN flag and acknowledgement flag, and the initial sequence numbers of both client and servers are selected randomly. And then the client machine replies with the help of a segment by setting the acknowledgement flag, and we can also send data with it. And we also try to identify the problem with this connection management mechanism in the form of Syn flooding attack. And the solution to the Syn flooding attack is also discussed, which is called a cookie, where the server generates the initial sequence number, not randomly, but as a hash of the source IP address, destination IP address, source port number, and destination port number, and a special secret number that is known to the server only. Okay, and we also try to discuss congestion. What is congestion, and what are the possible approaches to handle congestion, such as end-to-end congestion control, which is used by TCP and network-assisted congestion control. We will continue with the congestion control in the next class. Thank you very much. Allah Hafiz.